In fact, we have been talking about performance-based design for a long time. And these initiatives started in AIT almost 20 years ago when we started to work on projects of different kinds, starting especially with buildings. But before I talk about that, I want to start with an interesting story. A long time ago, when I started my practice as structural engineer, almost 40 plus years ago, I remember that I was engaged by an architect to do a medium rise building, almost, I think, 8 or 10 stories high. And at that time, the client wanted to meet the structural engineer. Normally, as you know, as architects, if you are an independent consultant, they normally do not, do that. But the client insisted that he would like to talk to the structural engineer. So when I had a meeting with him, his first question was that after you design the structure, is my structure going to be safe? And to me, the question was very innocent and very simple, and I should have a clear answer to that. But when I thought about it, I could not categorically tell him yes or no, because all I could tell him was that I have followed the appropriate design code. I think at that time it was ACI, I think 77, 31877. But beyond that, I could not give him any assurance that his structure was safe. And then I just told him that I have followed the code and you can check my design. He said, that's not my question. My question is, can you guarantee that my structure will be safe in earthquake, especially? And once again, I could not at that time, a long time ago, before all of these developments, I could not answer that clearly. And then, he was insisting that I give a certificate to its safety. So that has been in my mind, back of my mind since then, to see that we kind of rely on the codes to do most of the thinking for us, and we follow it. And many times we don't know the backgrounds, and we also cannot change what the codes have specified, and we are limited by a lot of the provisions in the code. But now things have changed. So let's start the discussion once again starting with the same question that I was asked at that time. So I'm going to start the discussion by the same question that is always on everybody's mind about, is my structure safe? Okay, so let's get back to the question of, is my structure safe? And see, first of all, let's start from the history, because this question has been there since the development of the infrastructure and the built environment. And if you look at the history, you will find that King Hammurabi, long time ago, about, almost 4,000 years ago, actually developed the first laws, and few of his laws also govern the construction industry. And one of the law, quite famous one here, says that if the builder builds a house for someone and does not construct it properly, and the house which he built falls and kills its owner, then that builder shall be put to death. It's a very severe categorical punishment for non-performance of the design on the construction, because the builder includes the structural engineer and everybody at that time. So as you can see here, that it doesn't say anything about building codes or anything. It just says that the builder is fully responsible for the performance, and if the performance is not good, the penalty is very severe. Luckily, we are not in that area. But now, at this age also, we must take responsibility for our work, but that is only possible when we have more clear understanding of what we are doing and more control on what we are doing. So first of all, why a safe structure is essential? And that is because of the disaster prevention. And we all are familiar with all these disasters happening around us. And disaster has these components, as you know, hazard, vulnerability, and exposure. And as engineers, we may not have much control on the exposure, also may not on the hazard, but we have control over the built environment and its vulnerability. And safety is part of that. So if you want to reduce the risk for the disaster, we need to reduce the vulnerability, because the hazard is not in our control that much. So vulnerability means that we need to make sure that our structure is safe, quote unquote. And because we have so many hazards around us, from earth, from water, from air, from fire, and more from man-made, that this is hard to put them all together. In fact, this multi-hazard assessments and vulnerability and risk is a major area of research for many people. But let's pick one of them for today, which is earthquake. And let's focus on how, as engineers, we handle earthquake or seismic design. So in Hammurabi's time or before that, there weren't any building code, no computers, no modeling, not even basic formulas, because they started something in the 16th century. So people just use intuitive design or intuitive construction through practice, through learning, and learn from there. So most of the things were just learned, passed from generation to generation, from one builder to his sons and his family. But then came the code-based design, almost less than 200 years ago. And then we start to see formal definition of what engineers should do, procedures, and all of that. So let's look into that. So if you look into that, how the building codes currently include safety is the first thing that we should look at, and then see whether there's something that we can learn from there. So building industry at these days, as you know, relies heavily on the building codes and standards, and because they specify the requirements, they give acceptable solutions, they also prescribe detailed procedures and rules and how to do this. And then mostly they are based on research, experience, but not always rational, because you will see later that some of the numbers are arbitrary or they are rounded, but based on practical considerations. And the spirit of the code is great, because the spirit of the code is to provide public safety and convenience. And the idea is that if we follow the code to the letter, the spirit of the code will be met. But there is no way to cross-check that. There is no way to verify that this is actually happening. We have to trust that the code, if you follow the code, we will get a good, safe structure. And the modern codes intend to ensure safety through estimated hazard or load level. So they will estimate how much live load there should be, or there can be, also estimate the wind pressures, wind distribution, and earthquake levels. And it used to be zones. It's getting better now. And then also they will describe the structural systems, members, which structural system you can use for which height, and so on. They will define procedures for analysis, which we will see today, and then provide rules for detailing, which is very important. And if you follow the rules and also follow the detailing and everything, then the hope is that it will lead to a reduced vulnerability and structural safety. So that's the overall picture of the design codes and their philosophy. Look at some of the requirements without going into details. As you can see here, that they are requirements with numbers, that you do this one, for that you do that one, for this one you do that one, the limit on the spacing of stirrups, 4 inches, 8 inches, rounded numbers, and for many places. And the intent, of course, is that we want to get a certain level of ductility and confinement and so on. But the exact numbers are not that critical, but most often they are taken to be literal. And if somebody doesn't follow and, let's say, provide the spacing 5 inches, not 4 inches, or 150 instead of 140 or 120, then we say, oh, this is not conforming to the code. And then we doubt the safety of the structure. So that's what happens, that most of the engineers, like myself at that time, I was hiding or sheltering myself from the responsibility by saying that I'm following the code. And a lot of time we still do that, from legal battles or whatever. We say, okay, as long as I'm concerned, I follow the code. You can check my calculation. If that is okay, that's all I can do. But that is not enough for the owners and the public. Owners will like to have many questions. Will the building collapse? Will it be damaged? Can I use the building after a given earthquake? How much will it cost to repair if it is damaged? How long will it take? Can I make the building that will not be damaged and will not collapse, like in some case? And then the structural engineers normally can say, yeah, I don't know about all of that. All I know is that I will follow the code strictly and I will over-design for you or something like that. But they don't have clear answers to most of these questions. Now, the one way that codes ensure safety is by looking at this basic, concept of capacity being greater than demand, which is a beautiful concept, which should be, and it's clear, until we see that this is not really, as soon as this is applied, then factors start to come in. We start to add the factor of safety. Sometimes people call it factor of ignorance, because we don't know anything or we don't want to know anything. And we say, okay, let me reduce the demand that we increase the demand, reduce the capacity, and so on. And then we can come up with ratio of the demand over capacity. And then we draw a line. One left side is safe, right side is unsafe. So as soon as the DCR ratio becomes 1.1, if our design is being evaluated by somebody else, they will say your design is failing, your design is bad, you did not do it well. If it is 0.99, it's fine. 1.2, So there is somehow a clear understanding that a little bit over the line, we are already into unsafe zone. But let's explore that further. If you look at the demand side is heavily modified through the process. The actual loads are very far from the demand that we compute for the DCR. We start with the real loads, we create load cases, we do the linear analysis, we have the actions, and then so on. And on the capacity side also, we have materials, we have assumptions they have, we have section, we have assumptions they have, we have theoretical capacity, we have capacity reduction, and then we come to the capacity. So both sides are heavily factorized before they are compared. And even after that, we insist that they should be within, less than 1. So if I expand that, you can see that there is a lot of work done or a lot of assumptions being made at each step of the process until we come to the final DC ratio computation. So obviously that DC ratio, the intent is great, but the computation has already, modified it drastically since it started. So you can't say I'm comparing the safety of the structure for dead load, because you can't really check that, because it's all been modified by load factors, capacity reduction factors, and so on. So this is one example. This is taken from the code itself. And it says that, okay, that green line is the computed capacity of a column section or a section subjected to, deformation in axial and flexural. And then the purple zone is the acceptable region. So according to the code, LC1, LC2 are safe, LC3 is unsafe, because this happens to lie outside the line. But it is still well within the theoretical capacity of the section. So if it goes out, it doesn't mean the structure will start to fail or member will start to fail, because it's still far from that. And that green line itself is not the theoretical capacity, the correct theoretical capacity, because it's based on assumed or design values of FC prime and Fy, both of which for the real case are through tests and observation and data have shown that they are expected values are always higher. So the real capacity will be somewhere out there. So that is based on expected strength without capacity reduction factors. So now we are comparing that blue line against that purple region, and we are defining our DCR ratio, DCR at that location. And we're saying LC3 is out. Actually, LC3 is well within the green and the blue. So the real problem will only come if this LC3 falls outside of the blue line. But obviously, that would require a DC ratio, 2 or 3 or something like that. So that's the first issue with the DCR computed on design like this one. But this is the probable capacity at site. Let's now go back to earthquake. That was just general, and see how this happens to an earthquake, say seismic design. And we are going to take the approach from ASC and ACI for this one. So this is the simple case, to talk about this one a little bit more detail. Let's say we have a small frame there, and let's assume that the wind load is somewhere there, the actual wind load. And then we will multiply the wind load by 1.7 or whatever, bring it to the design level after multiplication of the load factor. And that design level is where the yielding or the capacity has been defined, where we have calculated M phi Mn. So that is the point. And we are doing the green analysis, which is the linear analysis. So for wind load, it's quite straightforward. We are increasing the load to go to the design level. So we have a clear factor of safety present there. But seismic is very different, because seismic actual expected earthquake, the maximum earthquake, corresponding to the tectonics or whatever on the site, maximum credible earthquake over, low probability of 2%, let's say, is going to be very high, on a site which is governed by seismic. Very, very high. And elastic design will just never reach that. We will just have the structure undoable. And then that is reduced to a design basis earthquake by 2/3 of that to come to a design level earthquake from that. And then it is still too far from the design level of the capacity that we have talked about for other loads like wind and dead and so on. So it is further reduced by a factor, responsible reduction factor called R here. Other codes have different names for that, but that is so we are gone now. We have brought down the earthquake real loading down to the design level. Unlike the wind load, which was elevated, factored upwards, safety, we have to bring down the earthquake down to a level, which means we are already talking about an unsafe scenario. So the actual is going to be higher than design level in this particular case. So how do we manage that? That we bring that down, and we're expecting this to happen because of the ductility and damage and the nonlinear response. We're expecting that the structure will, after that portion, which is the limit, structure will continue to carry the load, but it will deform and it will damage, it will crack, the initial period will lengthen, damping will reduce and all of it, increase and all of that stuff. And then we say, okay, that red line will be there somewhere. We don't know the red line, so we're trying to guess it now. So we guess it by introducing a factor called omega, which is saying that, okay, design level for one member is there, but for the whole structure, because not all members will yield and the expected strengths are higher, and then we have over design because not every beam can be designed to the same exact value. We have to group them. Many beams will be over the design. So we put the omega overswing factor, and then we estimate that point. In fact, omega has 3 subcomponents, and sometimes we will discuss that. So this one is here. And then we have the net reduction of the demand RD from the design dB level earthquake down to the top of the actual structural response. And the problem is that R can range from 1.5 to 8 or even some less than 1. So there's a huge range here. Omega in the code can range from 1.5 to 3 or 3.5. So which means that there's a big range. Depending upon the choices of these two numbers, this red line could be anywhere in that shaded zone. So it could be as low as the design level or as high as the dB elastic level. Because if there is, so depending upon choice of these two factors, we don't know where this red line is. And that is the start of the biggest problem, because these factors are pretty arbitrary. And we have not considering the higher mode effects and things like that. So actually we can spend the whole day discussing the factors on this one because there is so much there to discuss. So if that is the problem, that means everything is highly approximated, and those factors, omega and both, are very specific to each structure. But the codes try to give us a table and try to put our structure there, but they don't really know exactly our structure. Especially the nonlinear response is so unique. So what if we were to remove everything and we just got the nonlinear response directly and remove everything from this slide? And you say, okay, let's just go to the structure and find out what is the capacity of the structure, nonlinear capacity of the structure. And then at the same time, we determine the reduced demand at the same time and say, okay, from the dB or MCE, I can come down and see where it hits my capacity curve or deformation curve. And then we can do the same thing for another level, for the service level. So we can ensure from the MCE that the structure will not collapse for the most probable earthquake ever to hit. And we can also assure that the structure will not damage at the most common earthquake that can come several times. So with these two limits explicitly checked, we actually cover all of the safety and the serviceability issues for earthquake. And that is what leads to performance-based design's basic concept. So we move from intuitive design to code-based design to next step on the ladder to performance-based design. So performance-based design basically now means that you can take the real materials, you can take the expected values of those materials, you can put them in the cross-section, or remember where the reinforcement has already been computed, and from the design basis, from maybe wind and other, and then you put this information, you calculate the nonlinear response of the section, like moment curvature and put the moment rotation, put those hinges, different kind, fiber hinge, this, and then we put that and we say, okay, now I have the structure which is almost going to be as built, as close to as built as possible. And this incidentally gives us the opportunity to also evaluate the existing structures. So that way, we can now do both. We can do the design and we can also do the evaluation. And then we go to realistic site-specific hazard. We look at the site hazard. We get the real data about what is the expected level of earthquake. We do the nonlinear pushover analysis. We do nonlinear time history analysis. Plus, we define some key indicators, and then we get a realistic performance evaluation. So that's how the PBD or PBE would work. So performance levels, now let's see how many performance levels you can have. So FEMA, long time ago, defined that we have operational, immediate occupancy, life safety, and collapse prevention as the key performance levels. And then we can check them all. And then the damage and loss is also measured on that scale. And then we can check them all back on the structural performance. So now we link hazard, vulnerability, and consequences. And we are close to solving that equation of the disaster or disaster prevention. So that's the whole. So we are actually explicitly going back to disaster evaluation, prevention, and vulnerability rather than only following the design through the code. Some of the key performance indicators that you can check is stiffness, stability, strength, deformation, drift, ductility, damage, damping, energy, and acceleration. And these can all be checked from the analysis that we perform, especially if you are doing nonlinear analysis. So that means that we have explicit limits and and clients or bodies can change those limits depending upon the type of structure, importance of structure, and so on. So now, go back to this picture again, where we said that we are hiding behind the code. If we change the code to PBD and PBE, then the whole slide will change. And the performance-based design and performance evaluation, and the engineer can say, yes, I can answer all these questions. So now we have full explicit knowledge and the tools to be able to answer all the questions of the public that we were unable to answer explicitly when we followed the code. So that's the main driving force why PBD and similar techniques are important. Now, the problem is how to convince other people. Okay, we are convinced, maybe you are convinced or not, I don't know. Let's see. But the issue is not us. It's about the stakeholders who are involved in the project. And those stakeholders, we have to start with the client, because the client is going to decide that, okay, I want my project to be done on PBD. And we had very good fortune on this one, because we started this in Philippines some 15 years ago. We were very fortunate that one of the clients in Philippines agreed to say, okay, I'm going to try this PBD with you. And he asked me at that time, I remember that, okay, what is the benefit to me? And I told him that you can tell the public that your building has a higher performance and certified performance than the other building. He said, will you write a certificate for me? And I said, yes, we will write a certificate for you. At that point, after 30 years from the first time, we were able to say that, okay, we will write a certificate for you. So he then was willing to pay for all these things. And then watching him, other clients also joined. And since then, our ASD Solutions and our team, AIT, has been involved in more than 200 tall buildings, performance-based evaluation and design. It was just convincing one, and then other people just started following. So once you do that, you have to work with the architect. Structural engineer on record has to work with a PBD specialist who is specialist in doing this one. Then we need to work with a site-specific consultant who does the PSHA for the site. And then we definitely need a PBD reviewer, because this is very involved analysis. Somebody third party, better knowledge than the PBD consultant, should review this. And once all that picture is complete, then we have a good PBD sort of project completed, and something that everyone can trust. So let's quickly go through what else is lying ahead of us. Actually, it's not future; it is already present in many places. So from the performance-based design, there's a consequence and risk-based design. Mostly the insurance industry is interested in this one. They would like to reduce the insurance cost if you know that the building has a better risk prevention. And then from that, we have the resilience-based design, which is much broader than that. And a lot of work has been done and is being done on that, including the non-structural damage, including many other things. So it's just something that we are on the way to that. So coming back to this diagram one more time, in this diagram, we assume that the wind load was below the seismic design level load. But what if we have a wind load which is much higher than this demand? This opens up a whole new difficulty in this PBD because the factor R and omega are now, as computed, are not going to be valid because you cannot have the design level, seismic design level below the wind demand level. So it is leading now to the adoption of seismic design, which is now going to the resilience-based design, and wind is also following, so that people are saying, okay, if you're doing the seismic design PBD for seismic, why we should not do the same for the high wind, like return period of 2,000 or 1,700 years or more. So making them similar. So in the new movement or new guidelines are coming up. So people are now saying, okay, wind design is what we can do, also using PBD. And finally, let me just conclude by saying that the structural engineer, we should be answering bigger questions. First one, what is the purpose of structural design? We should really not just say that I'm going to put the reinforcement. What is the ultimate big purpose? And that is, as I mentioned to you, resilience, sustainability, and all. That's the ultimate goal, to reduce increase the resilience and reduce vulnerability, and also increase sustainability. Because when you are using the smaller sizes, you use less material, your carbon footprint goes down, and you have better, environmental sustainability. How to achieve this design purpose? Once you have the design purpose, we should have a clear idea how we are going to do that. And then, more important, number 3, how to confirm that the design purpose has actually been achieved. It's easy to say that I'm going to do this one unless it is checked and confirmed. So that is what we talked about, that PBD and PBE actually helps to do that. And then the next one is what to do if the design purpose is not achieved, how to go back and fix it. And then once again, so we have to work on that. And finally, what is the consequences if the design purpose cannot be achieved for whatever reason, cost or whatever? We should be able to tell that, okay, this cannot be done. This is the solution to that. So with that, I come to the end of my part. Thank you so much.